Hello everyone, welcome back to vishnusmartinfo. I hope you all are doing good. And in our last video, Gravitation Part 1, we have successfully completed it with Kepler's law and Newton's law of gravitation. I hope you follow the next video which I posted on few questions. Also, I posted few questions on Telegram, and also I hope you checked out the notes which I posted on Telegram. So today is the second part of the gravitation chapter, and we are proceeding today with relation between G and capital G. So what is small g indicating? It indicates acceleration due to gravity on Earth. And what does capital G indicate? It indicates gravitational universal constant. So how do you derive a relation between G and capital G? So you need to consider, let us consider our planet Earth of capital mass M and having radius capital R. Now I am considering a small block of mass M on it placed on the surface of the Earth, and we know that the weight of this block will be acting downwards towards the center of the Earth as mg, and this is the weight of this block. This we can equate with the gravitational force which is existing between the capital mass M and the smaller mass m. I told you in this gravitation chapter, whenever you find any type of force, weight, let it be tension, let it be centripetal force, you just need to equate with gravitational force. So similarly we do it here. So we equate with gravitational force. How do we represent gravitational force? G into capital mass M into small mass of the block. What does capital mass M indicates? The mass of the planet or the Earth. And the distance between the Earth and this small block we can consider from the center of the Earth up to the surface, so which is nothing but the radius. So we do radius square. So when small m gets cancelled, so small g is equals to capital G into mass of the Earth upon radius of the Earth square. Okay. So sometimes this may be the distance, sometimes it may be the radius. So you need to consider from case to case. So this is the relation between the small g and capital G. This should be on your tips. It is very important. So now for this relation also there are two cases. Now as we know here, this is the mass. Now this mass can be represented in terms directly as mass, or it can also be represented in terms of density. So that's why there are two cases for this formula. The case 1. In case 1, what do we consider? Where mass, capital mass M is constant. What is capital mass M? It is the mass of the planet. Okay, it is the mass of the planet. So that is constant. So when capital mass M is constant, you will get that G is inversely proportional to R square, because capital G is also a constant and capital mass M is also constant. So G is inversely proportional to R square, and I already told you when such cases arrive where G is inversely proportional to 1 by R or 1 upon R square, the graph is hyperbola. So the graph between G and capital R will be a hyperbola. So this was our case 1. Now coming to the case 2. Case 2. In case 2, what we will consider? Density to be constant. Density to be constant. Now you know that mass is equals to density into volume, right? Now here volume of the sphere will be d into 4 by 3 pi r cube, right? So if we substitute this m in terms of this in this formula, what do you get? G is equals to capital G into this term, d into 4 by 3 pi r cube upon r square. So r square and r cube gets cancelled, remaining 1 r. So you get G is equals to capital G into d into 4 by 3 pi r. That's it. So from this, G is constant and we consider density to be constant. 4 by 3 pi is constant. So G is directly proportional to R. So here what will be the graph like? The graph between G and R will be a straight line passing through the origin. It is passing through the origin. Okay. So I hope you got the two cases where one is mass is constant and in the other case density is constant. Okay, don't worry about notes. I am just roughly explaining you. Notes will be surely posted on Telegram channel. Up to date, you can follow the link from the description box below. Okay, so there are two cases. Mass is constant, G is inversely proportional to R square. Density is constant, G is directly proportional to R. And G, here the graph is a straight line and here the graph is a hyperbola. I hope I am very clear. So now let's proceed with another topic, that is variation of G in different cases. So what is G? I said you it is the acceleration due to gravity. Now there mostly in the questions will be asked the three different cases with respect to this G. That is with respect to height, with respect to depth and with respect to latitude. So let's proceed with the first one, which is height. So you just need to follow one form in like this is a modification of this formula itself, Gm upon R square curve. This is a modification. What you need to consider, instead of placing the mass, that small mass which we kept on the surface of the earth, we are not placing now it at the surface of the earth, but we are placing it at some height h from the surface of earth. That's it. So now what will be the distance become? Gm upon R plus h whole square, because this is from the center of the earth you always measure the distance. So what will be the total distance? R plus h whole square as it is. That's it. Okay. So this is one formula. Now in this cases you know that one thing you need to remember, or sometimes it is provided in the question, that R is equals to 6,400 kilometer radius of the earth. Okay. So now suppose h is given as 3600 kilometer or 1200 kilometer like this. Then you need to apply this formula, because the h is comparable to R. But sometimes if h is like only 2 kilometers or only 4 kilometers, very small values, okay, comparable to R, it is a very small value, right? 1 kilometer or 2 kilometer. That time the modification of this formula is G at that particular point is equals to G at the surface into 1 minus 2h upon R. This is the formula. So in height cases you need to remember two formulas. And what is this G? This G is equals to Gm upon R square, which was at the surface. This value is for the surface. Okay, this G. And this G is at that point, at that height, at that particular height, G dash into 1 minus 2h upon R. Suppose h is 1 kilometer or 2 kilometer and R is 6,400 kilometers, or else they will mention in the question. So this formula will mostly be asked to find the ratio. They will ask you what is the ratio of gravity, what is the ratio of acceleration due to gravity at a height 2 kilometers from the surface of the earth as compared to the surface of earth. So they are asking you G dash upon G ka ratio. Bring this G here and calculate 1 minus 2h upon R. That will be your answer. Okay, so these questions will be mostly asked in the terms of ratio. Direct values they will never ask. Okay. Next, coming to the second case, which is about depth. In depth, there is no modification of formula. There is just one simple formula, that is G at some depth. GD I represent. Here also I will represent as GH. GD at some depth, the gravity at some depth is equals to gravity at the surface into 1 minus D upon R. Okay, 1 minus D upon R. So how do you represent with this diagrammatically? Suppose this is your earth and you were on the surface. Now you are going at a depth D. At a depth d inside the surface. At that particular point, what is the gravity you feel, what is the acceleration due to gravity you feel, that time you need to use this formula. There is no modification in this formula, direct this formula is applied. Okay. Next, coming to with respect to latitude. Latitude means angle. I hope in class 4th or 5th you have studied about latitudes and longitudes. Latitudes are horizontal lines which run from west to east, and they are imaginary lines to locate some places. So for example, this is your earth and these are your latitudes. So if suppose from equator or center of the earth you are standing here, so at this particular angle, which you make with the center, what is the gravity you are feeling? And of course the earth is rotating at its own speed, at its own angular velocity omega on its own axis. Then at this particular latitude, what is the gravity you are feeling? For that you have gravity at this particular angle, g pi is equals to g into g minus r omega square cos square pi. This is your formula. G minus r omega square cos square pi. Okay, this is your formula. G minus r omega square. R is the radius of the earth, omega is the angular velocity of the earth, pi is the angle, and you are taking cosine of it. Okay, so this is the formula. I hope these three cases are very clear, simple, easy. You will directly see this in question. Gravitation is a chapter where you need to remember simple concept, simple formula, and you are good to go. Okay, no need to worry. Just simple 3-4 formulas you need to remember with respect to G in different cases. One formula is G is equals to Gm upon R plus H whole square. The second is this modification of this formula, and then depth, and then latitude ka formula. It's very easy, clear? Okay, so in this formula with respect to latitude, what is the formula? G pi is equals to G minus R omega square cos square pi. In this formula also you will have two cases. Okay, that is at equator. At equator your latitude angle will be 0 degrees, and at poles the angle will be 90 degrees. Okay, so just substitute that in formula. So G pi is equals to, so cos 0, the value turns to be 1. So G pi is equals to G minus R omega square. So at equator what is happening? This G, I meant the acceleration due to gravity at the surface. Now at equator R omega square is getting subtracted from it. Means that G pi value is decreasing. Means at equator you will find it to be minimum or less value. But at poles, cos 90 is 0. The whole terms get cancelled. Means it gets 0, na? R omega square into 0. Something into 0 is 0. So G pi is directly equal to what is the gravity at the surface. Right? That's what, na? When you see here, this is your surface. This is your earth surface and nothing but these are the poles. 90 degrees at this point or at this point. So that's why at here and here the gravity is maximum. So at poles the gravity is maximum. These two cases easy. Okay. Now sometimes in question they will ask you about weightlessness. And they will ask you what should be the weightlessness, and they will ask you what should be the omega value to feel weightlessness. That time what you need to do in this formula, G pi is equals to G minus R omega square cos square pi. Equate this to 1. Okay. Not 1, you need to equate this to 0 because you are feeling weightlessness. Means G pi, there is no gravity. Weightlessness means what? Weightless. You are not feeling any weight on yourself. So the gravity, acceleration due to gravity value turns to be 0. So this formula you need to equate with 0. So G is equals to R omega square cos square pi. Okay, easy. So now what will happen here? Cos square pi ka value also you can consider to be 0. We will consider this value to turn as 1. this value to be turning as 1, because weightlessness questions will be mostly asked for equator only. At only this particular level they will ask for equator only. So at equator we know that pi is 0. So see, I will repeat once again. In weightlessness, the questions will be mostly asked with respect to equator. What they will ask, that at equator the person is feeling weightlessness. What is the omega value? What is the angular speed of the earth? That's it. That will be the question. So what you need to do, that g pi is equals to g minus r omega square cos square pi formula is there, no? So he is feeling weightlessness. The person is feeling weightlessness means what? That there is no acceleration due to gravity at that particular point. So this formula will be equated to 0. So when you solve this, what will happen? G and r omega square cos square pi will come to this side. Now as it is said that it was on the equator, so cos pi value, if you put pi as 0, so cos square 0 value will be turning as 1, right? Cos 0 is 1. So g is equals to r omega square. So g by r under root is equals to omega. So this will be your omega value. Okay, like these questions may be asked in your objective. So let's proceed further with another topic, gravitational field strength. So what does something with related to field strength? Always remember field means what? Like your cricket ground or something. So it is an area where you particularly feel the presence of being there. Like when you are in a cricket ground, you feel like playing cricket. Okay. So or whenever you are at football ground, you feel like playing football. And you are in an area where football can be played. Similarly, whenever the field is talked, when we say field, it means a particular region where you can do that particular activity. So now gravitational field is everywhere. It is present everywhere on the earth. Okay. And always the gravitational attraction or gravitational attractive forces are always present between two masses. So when you consider the gravitational field, in this field where gravitational activity means the gravity is acting. Gravitational field means what? In that particular field, gravity is acting. There is some attractive forces between the masses. That's it. So in this field, when I am putting a small mass m, a small unit mass m, whatever the force is acting on this unit mass m, unit mass 1 kg, whatever force is acting on this unit mass m, whatever the forces, suppose there are so many bodies over here, one body here, one box here, another 2 persons here. These all are having masses, right, in this gravitational field. So I am placing one small unit mass m. There will be some gravitational force between this person and this mass. Again with this box and this mass. Again with these 2 persons and this mass. So there are gravitational forces between them. So how much force is acting on this particular unit mass m is nothing but your gravitational field strength or gravitational field intensity. Gravitational field intensity means how much intense ga akkada force undi. Okay, on that particular mass, small mass m. And this is a vector quantity and the SI unit for is Newton per kg. Directly from here. What is the units for force? Newton. What is the units for mass? This is mass. Okay, not meters. Mass. So what is the unit for mass? Kgs. So SI unit will be Newton per kg. One more way is there where you denote F, where you will denote in terms of potential and distance. We will talk about that later. But till now you need to remember this only. So gravitational field strength or intensity, it means gravitational force on a unit mass m. Okay. And this gravitational field strength will be denoted with letter E. And what, as it is a vector quantity, it must of course have a direction. So what we will consider the direction for it? In the direction of force. Suppose force is acting in this direction, then E will also act in the same direction. And always remember, gravitational force is attractive force. So towards the body. Always it will be towards the body. So now sometimes they will ask a questions on null points. Okay, what are null points? Null points. Null points means there is no gravitational force or gravitational field at that particular point. Okay, null points are those points. So consider, so there will be two cases. Null point asking between the bodies and null point asking outside the body. So for most of the cases there is no possibility of getting a null point outside the system. Okay, always the null point in gravitational chapter especially, the null points will be between the bodies. It will never be outside the body. And to find null point, you just need to apply the concept of this E only, gravitational field strength only. What you do, you take your unit mass small m and place at one particular point. If this unit mass m at that particular point is facing no force acting on it, then we can say that there is no gravitational force at that particular point. Okay. So for example, what I do, I take one mass of m1 and I take another mass m2 and they are separated with a distance capital D. Now what I do, I take a small mass m, one unit mass m, and I place it here. What I will observe, now you tell me, I said you there will be some gravitational force between the masses. So what will be the gravitational force between the small m and m1? You can denote by F is equals to G into m1 into m upon distance between them. That's the square of the distance between them. That is okay. But if I ask you in terms of E, what is gravitational field strength? What will be the direction of it? It will be in the direction of gravitational force, right? It will be in the direction of gravitational force. Now this m1 mass and this m, I said you with whatever respect body you take, suppose I am considering here this small unit mass m. So on this small unit mass m, what is the gravitational force due to m1? It is directed towards this side only, no? Because it is always attractive force, right? Similarly for m2, it will be also directed in this direction, because this will the gravitational force between m2 and m will attract the small mass towards m2, and m2 will also get attracted towards it. Similarly m1 will also get attracted towards it, and m will also get attracted towards it. So always it is towards the body. So in this case, what you see, that if I am putting a small mass m outside the system, this was my system, and I am keeping a small mass m outside the system, what's happening? So the E, this is the gravitational field intensity with respect to first body, and this is the gravitational field intensity with respect to second body. Both are in the same direction, they will get added up. Now is there any chance of getting them cancelled? No. So you can confer from here that there is no null point if you place a small unit mass m outside the system. Similarly, you can try this for this side as well. You can try for this side also. If I put this small mass m, now tell me this, if I put here, now the E value, now these arrows will also change. Now this this m2 will be attracted towards this m, and this m will be attracted towards m2, so like this. And similarly this m1 will be attracted towards this small mass m, and this will be attracted here. So here also E1 and E2 will get added up. They will get added up, right? Easy. Now similarly, if what I do, I will put this small mass m between the bodies. Now you will see some difference. This is small mass m1. So now I kept the small mass m between the bodies. I kept them between the bodies. So the two bodies m1 and m2 in our system is separated by capital D, and the small mass is placed at a x distance from m1 and d minus x distance from m2. Now what you will see, this m1 and m, they will be attracting towards each other due to gravitational force. So this is E1, field intensity 1, and similarly the m2 mass. So it will be towards each other, attracting towards each other, attracting towards each other. So now there is a possibility of E1 and E2 getting cancelled if they both are equalized, right? How can I cancel these both? When they both will get equal, E1 and E2 on this small mass m. And once E1 and E2 gets equal, means this small mass m is pulled from both the sides, and finally it's not getting moved neither this side or neither this side. It is staying constant at that particular point. It means what? That there is no net force acting on it. What do you call force? It is a push or a pull. It must be pulled this side or it must be pulled this side. When it is not moving, E1 and E2 is getting equal, means there is no gravitational force at this particular point. And this particular point distance you can find from M1 as x and from M2 as d minus x. So what you will do? You will equalize so that E1 minus E2 gets subtracted, which is net field intensity is 0. So E1 is equals to E2. Now what is E1? So what is gravitational field intensity? It is force upon unit mass m. So how do you write force? G into mass into small mass m upon distance into, now this small mass m for intensity. Small m will get cancelled. So how do you write that? Capital G into m1. You will not consider this unit mass m because we are considering E1 as force upon unit mass m. So that small mass m will get cancelled. So G into m1 upon distance between them is x square. And similarly G into m2 upon distance between them is d minus x whole square. Okay? Easy. So from when you solve this formula, you will get the x value according to the question. So like this you will find null point. So let's move on to our next application of gravitational field strength. So this we will learn in a comparison manner of solid sphere and hollow sphere. So these are very important to learn applications of gravitational field strength of solid sphere and hollow sphere, and to learn potential applications of solid sphere and hollow sphere. Potential wala we will do in further part, but first let's learn about gravitational field strength. So starting with solid sphere, so let us consider a solid sphere. Solid sphere means it is composed of mass, full inside mass is there. Hollow sphere means inside no mass, only at the boundary mass is there, inside it's air or empty. Okay. So coming to the solid sphere, so what is the, just you need to remember how the gravitational force will act, or gravitational field strength will act on the solid sphere, like with respect to at different points. So I am considering the solid sphere of capital mass m and capital radius r. So now if I place a small, so what will be the gravitational field strength at a point outside the solid sphere? E out. The gravitational field strength at outside the sphere you will write is equals to G into mass of the gravitational constant into mass of the sphere upon distance. How much is the distance? R square I am denoting. Okay. Now what will be E at the surface? Just this R will get replaced with the radius of the solid sphere. The distance now with the surface is this much only, no R only, no capital R, which is the radius. So G into M into capital R square. Inside the solid sphere it will be, there is a different formula little bit, G into M into small r. At what small r distance? That what small distance from the center you are considering inside. Inside means at how much distance? Let me replace this with A. Okay, so not to get confused, I will write here A. So inside at how much distance? Upon r cube. And E at the center, if you place A value 0 here, this whole term will get 0, no, because A value will be 0 at the center. So E center will get 0. So these are the four cases for solid sphere. At surface it is Gm upon r square. At outside it is G into M into upon r small r square. What is the distance? At inside it is G into M into what is the distance upon r cube. And E center will be 0. Now remember the graph. In graph you can see from formula only. I will write this as E again. So here E inside is directly proportional to this distance A. This is capital R is the radius, But here it is directly proportional because this radius is constant, mass is constant, g is constant. What will change is a only. So E inside gravitational field intensity inside is directly proportional to a. So it will be a straight line up to the surface. The graph will be in a straight line up to this surface. From the surface it will turn to be again hyperbola because it's inversely proportional to r square. Okay, E out and E surface, from the surface it will turn to be a hyperbola. Now coming for the hollow sphere. For hollow sphere, it's already the shell theorem I have explained in the previous video. Again I am explaining. For a hollow sphere you need to consider the whole mass is concentrated at these boundaries, but only for E outside case you will consider the whole mass is located at the center. So for E outside case you will get like normally only gm upon r square. But for other cases, like for E inside, you will get 0. Inside there will be no gravitational field intensity due to the shell. Okay, so if your body is placed inside hollow sphere, it won't feel any gravitational force acting with respect to shell. But similarly, if I place this small body m in a hollow sphere, it won't feel any gravitational force. That is correct. But suppose if I put capital mass m outside the sphere, now it will start feeling a gravitational force due to this mass m, not because of the shell. If this mass is removed, again gravitational force on this will become 0. Okay, so once it is placed inside the shell, there won't be any gravitational force acting. Okay, and E at the surface is just like normal gm upon capital R square. And how do you draw the graph? So there will be no graph for inside because inside the E value turns to be 0. Only for outside, from the surface you will get a hyperbola graph is inversely proportional to R square. So we'll just compare them. E at the surface, same only. E outside, here it is gm upon distance square. Here also it is gm upon distance square. Here E inside is gm into a upon r cube. A is the small distance, up to what distance you are considering. Gm a upon r cube, and here E inside is 0. And here E at the center is 0. Here also E at the center will be 0 because it is a inside point. Inside anywhere it is 0. Okay. You can see graph is like this, and here only the hyperbola part. So this is very important. You can just take a screenshot as well. This is very important. So next topic is gravitational potential. So let's move on to the next topic, gravitational potential. So in gravitational potential, what is potential? Potential means how much work we can do, right? We will say, no, we have more potential than yours. So potential means work done. So gravitational potential, it is in the field. Again, we will consider the gravitational field. In that, it is the amount of work done in bringing a unit mass from infinity to a particular point. So like from a distance, very large distance, infinity to this particular point, let us consider this distance to be d. So we are bringing a small mass m, a unit mass m, to this particular point. We are doing some work done. That work done is called as gravitational potential. Now as it is work done, it is obviously a scalar quantity. So how do we write work done? Work done is equals to force into displacement. Right? Force into displacement. And here it is unit mass. So divide upon unit mass. So how do you write gravitational force? G into capital mass m into small mass m into how much is the distance? Let us consider here d square, gravitational force, into displacement is again same d only, upon small unit mass m. Small m gets cancelled, dd gets cancelled, so gm upon d. So this is your gravitational potential. We will indicate it with v, letter v, which is equals to g into mass into upon d, the distance which you are bringing it. It is a scalar quantity. Okay, easy. So gravitational potential is a very important concept. You will need it to solve different types of sums. They will say you that gravitational potential at that particular point is this much. Find the distance between the body. So just put this formula and get. And now one more thing interesting. The sign of this gravitational potential will be negative. Why? Because see, work done. Now this is a work done. Now work done will depend upon which type of force we are using. Here we are using gravitational force, and you know that gravitational force is attractive force. So obviously attraction means negative. So the sign comes to be here negative sign. Negative means attractive forces. This attractive forces, it is due to gravitational forces. Now for this gravitational potential also, as I said, you will have two cases for solid sphere and hollow sphere. So this will be the today's last topic. Then we will continue in our next class. So the last topic is between solid sphere, gravitational potential concept, and for hollow sphere. Solid sphere and hollow sphere. Okay, so for solid sphere and hollow sphere, let's learn about the potential concepts. So potential for a solid sphere, let us consider of mass m. So at a point at a distance r from the center of the solid sphere, at a distance r outside the sphere, you will write in just how we write potential. V is equals to minus gm upon distance, like that only. So distance is r, small r, minus, because to indicate attractive gravitational force, G into mass of the solid sphere. Now for V at the surface, it will be equal to minus into G into mass of the solid sphere into capital R, because the radius of the sphere is capital R. So this distance is capital R. Again, for V inside it will change. For V inside there will be a different formula. Like for E also you had a very different formula, like G M A upon R cube. Like that only here also for V inside of a solid sphere, you will have this formula and you need to remember this. So this is equals to minus Gm upon R cube into 3R square minus R square upon 2. Well, now what is this R square? Again I will change this letter with A. So no confusion. A is equals to 0. Means at what A distance you are considering from the center, inside point. So that distance. And always don't forget to put the negative sign. Now if I talk about E at the center, A value turns to be 0. So if you substitute A equal to 0 in this formula, this is minus symbol, A equal to 0 in this formula, you will get V center is equals to 3 by 2 times of V at surface. V at surface is Gm upon R. So V at the center will be 3 by 2 times of what is the potential value at the surface. Okay, easy. So at the center the potential is greater than the at surface, because 3 by 2 is 1.5. So at the center the potential is 1.5 more than the potential, 1.5 times more than the potential at the surface of a solid sphere. Now coming to a hollow sphere concept. In hollow sphere, V out will be again same simple formula, minus Gm upon R, and V surface will also be same, minus Gn upon R, but the distance capital R will be the radius. What capital R radius this distance you are taking. And V inside. Now this is an interesting. As we know in hollow sphere means inside air is there, and we know that inside the gravitational field intensity is 0 on any body. Gravitational field intensity inside is 0. Now if this is 0, there is a formula called E is equals to potential upon distance. So you will learn this formula in electricity chapter, and this is very important relation between potential and something field. So this is field intensity is equals to potential divided by the distance. So you know that E should be 0. The intensity should be 0. How it will come 0? When something's constant differentiation is done. When you do a, like so for example, 2 is there. For this 2 is a constant value. This constant value, if I do differentiation with respect to anything, with respect to distance I do, or with respect to time I do, whatever differentiation for this 2 I do, answer will be 0 only, because the differentiation of a constant is 0. So similarly, you need, from this formula you can say that as E is turning 0, in the hollow sphere there is no gravitational field, means potential is constant, because differentiation of a constant is only 0. That's why we conclude that inside potential will be zero, sorry, not zero, it will be constant, it will be a constant value. And how much that constant value will be equal to? It will be equal to the potential which is at the surface. So how much potential you will have at the gravitational potential you will have at the surface, the same potential will be there across the inside the hollow sphere. So if the question is asked, are there any points existing no field intensity but potential is present? If they ask some question like this, no intensity but potential is there, yes, inside a hollow sphere there is no why I'm getting electric field, gravitational field intensity, but gravitational potential is present. Okay, easy. I hope this is very clear. So that's it for today's class. So we learned, if we do a quick revision, we learned about relation between G and small g. So what all we learned in today's class? We learned about relation between G and capital G. Then we learned about G in different cases. Then we learned about electric field strength, gravitational field strength, and we also learned its application for solid and hollow sphere. Then we learned about potential, and we also learned its application for solid and hollow sphere. So these 4 topics for today's class. That's it. And what will be your homework? Your homework will be just giving a quick NCERT reading as a novel, and then proceeding with NCERT back sums, and then whatever module you are having, those sums you should do. So, and by tomorrow I will post my notes video. You can follow them and make your own also. I will be posting in the Telegram channel. You can get the link from the description box. I will be posting the link in the Telegram channel. I will posting my notes, and you will also get few questions to do on these topics on the Telegram channel. So do join that channel and also subscribe to this Vishnu Smart Info channel. Thank you. Have a good day. Bye bye.